Hello, pals. Today we are discussing velocity time graph. Now, velocity time graph is one of the major parts of kinematics. And don't forget that kinematics is also a major part of mechanics. Now, I've been on this series for quite some time. And with this very lesson, we draw very close to the end of this very series under kinematics. So, when we talk about velocity time graph, now, velocity and time, they are well known. Velocity is a physical quantity, and not just a physical quantity, it's a derived quantity. Time is a fundamental physical quantity. But when we talk about graph, what is graph? Now, graph is a major thing. Like I say, graph is a major tool that is being used to explain an ideology, that is being used to explain a concept. Now, when we talk about graph, graph is not only applicable in physics, graph is applicable in mathematics, it's applicable in economics and in most social science and stuff. Each time we have data, graph becomes handy or useful. So when we talk about graph, in order for us to understand a phenomenon or an idea, we bring together all the parameters, all the things that make up such an idea or concept, and we put them into the y-axis and the x-axis of every graph. So the y-axis is known as the ordinate, the x-axis is known as the abscissa. So right here today we are discussing, a major quantity known as acceleration. Now, acceleration is a derived physical quantity. So we're going to be explaining what acceleration is by bringing together the two major parameters, which are the velocity and the time that make up acceleration. So we're going to be doing that, using the y and the x-axis of a graph, of a given graph known as the velocity time graph. So each time velocity and time are being brought together, that means you're about to explain acceleration. Don't forget, acceleration is equal to change in velocity over change in time taken. And each time displacement and time is being brought together, that means we are talking about velocity. So the way we are discussing velocity time graph, we could also discuss displacement and time graph. So quickly, let's see what we have here. We have three various samples of time graphs. So the first we have is a time graph that shows uniform acceleration. Uniform acceleration. So here, right here, we have velocity, which is in meter per second, and we have time, which is in seconds. So for velocity, now the very first that we have, as you can see, this body started from rest, that is 0 meter per second, that's from rest. At this very junction, you can see we call this the origin or the reference point. Why do we call it the origin or the reference point? It's origin because of the fact that everything starts from here. Everything starts from here. The velocity starts from this junction, that's from the very place, and also the time, which is 0 seconds, also starts from here. So the body moved from this very point to point A, covered 6 meters per second. It took it 3 seconds to do that. So as you can see, that there's an acceleration of 2 meters per second squared. And also it moves from point A, I beg your pardon, to point B, that's 6 meters per second down to 12 meters per second. And it took it another 3 seconds to do that. That's from 3 seconds to 6 seconds. So you also have an acceleration of 2 meters per second square, as you can see, 6 to 12, which is change in velocity of 6 meters per second, 3 to 6, change velocity of 3 seconds. So the same thing happened, at the very third point, which is from 12 to 18 meters per second. That's a change velocity of 6 meters per second, and 6 to 9, a change in time of 3 seconds. So we call this uniform acceleration. So when we talk about uniform simply means the result of the acceleration we get at every point in time. Now this is an instantaneous acceleration we are talking about. At every instant, the acceleration we get is the same thing. At point A, acceleration 2 meters per second squared. At point B, acceleration 2 meters per second squared. At point C, acceleration 2 meters per second squared. That's why we call it uniform acceleration. Acceleration does not change here, it's uniform. So the next thing we're going to look at is uniform retardation. Now, acceleration and retardation or deceleration are simply the same thing, but the difference here is that for acceleration, there is an increment in velocity, but for retardation, there is a kind of decrease, a kind of decrement also, or we could use that in velocity. As you can see this, the velocity of this body was 18 meters per second, and all of a sudden it dropped down to 12 meters per second. Initial velocity 18, final velocity 12 meters per second. That took it 2 seconds. So as you can see, that is deceleration. Deceleration is kind of acceleration actually, but there's a decrement in speed or velocity. So from 18 to 12, change in velocity is 6, change in time is 2. So what do we have there? We have we have 3 meter per second squared in the negative direction. And also, if you look at from point A to point B, as you can see, 12 to 6. From 12 to 6, the body also reduced in speed. And it took it also another 2 seconds for this to happen. So we call this uniform retardation. So when we talk about uniform, there is a change in speed over time taken, but the result gotten for each change is constant and it's uniform, I beg your pardon. And that's why we call it uniform acceleration or uniform retardation. So right here is what we call the constant velocity. As you can see, the body moves in a straight line. Now there's a big difference between constant velocity or constant acceleration and uniform acceleration or uniform velocity. As we set it up there, that for uniform velocity, the body, we keep getting the same result. Acceleration, we have acceleration sure for that we have acceleration for sure, but the result we keep getting at different points, we keep getting the same result. For every change in velocity over change in time, we keep getting the same acceleration. But when we talk about constant velocity, for constant velocity, there's no acceleration at all. The initial word velocity is the same as the final velocity. That's the big difference between constant velocity and probably constant acceleration and probably uniform acceleration or uniform velocity. So we have to understand this concept before we move directly into our calculations. Okay, guys, it's time to look at some worked examples. So right here we have the first question, which is a body at rest is given an initial acceleration of 6 meters per second squared for 20 seconds, after which the acceleration is reduced to 4 meters per second squared for the next 10 seconds. The body maintains the speed attained for 30 seconds. Now we asked to get a couple of things. Now the first thing we have to do is to draw the velocity time graph for this very question, this whole scenario. And the next question, find the maximum speed attained during the motion. Then the third question, find the total distance traveled during the first 30 seconds. And the very last question, find the average speed during the first 30 seconds. Now this question was given to some YX students in 2009. Now this is a very interesting and quite witty question, but it's very, very simple. Now the first thing we're going to do, according to the very first question, is to get velocity time graph. That's the first thing. Now if you look at the very first statement, a body at rest is given an initial acceleration of 6 meters per second squared for 20 seconds. Now don't forget, they didn't state the velocity attained. They only gave us the acceleration. Now don't forget that before we can have an acceleration, it means there is surely a change in velocity. There's a kind of change. That means the body moved from one speed to another speed. So let's try to interpret what that means. So first of all, we all know that acceleration, which is a change in velocity over time. So acceleration already is given as 6 meters per second squared. So that's 6 meters per second squared, which is a change in velocity over the time that it took that body 20 seconds to get to this velocity. So you're going to cross multiply. So change in velocity right here is 20 times 6, which is 120 meter per second. That's what the change in velocity is. So we're going to try to draw our velocity time graph. So the body started from rest. Don't forget, the body started from rest. According to that, this is a reference point. So the body started from rest and got to a maximum speed of 120 meter per second. So the body started from here. Body started from here, and attained this very speed. The body attained this speed. Let's see what the body did. Body attained this very speed. So the body got to this very speed, the speed of 120 meter per second. Now it took the body how long? It took the body 20 seconds to get to this very speed. From no speed at all, from a body being at rest to a body attaining 120 meter per second. So it took the body just 20 seconds. That's from rest 0 to 20 seconds. So don't forget, from rest to 20. So don't forget that the body was also at rest. It wasn't moving. So from 0 meter per second, the body moved down to 120 meter per second. And it took the body 20 seconds to achieve this. Now, if you look at the next line of statement, it said that for 20 seconds, after which the acceleration is reduced to 4 meter per second squared for the next 10 seconds. So a body that moved virtually from 0 meter per second, speed to 120 meter per second speed for 20 seconds. This whole thing lasted. So that body then, came down, reduced the speed. Now don't forget that it was said that the speed was reduced to 4 meter per second squared. Now, the speed, the acceleration, was reduced to 4 meter per second squared. From 6 meter per second squared to acceleration of 4 meter per second squared. It means the body kept on accelerating, but lost some speed, during the course of acceleration. So let's try to interpret that. Now don't forget acceleration as usual. Acceleration as usual, as stated up here, this is vector quantity. Acceleration is change in velocity over probably, change in time over time. So if acceleration reduced to 4 meter per second squared, so that would be 4 meter per second squared, which is change in velocity over time taken. How long did it take that to happen? It took the body 10 seconds to achieve that. So that means we have a new velocity of about 40 meter per second. So let's simply see what happened. The body acceleration reduced from 6 meter per second squared to 4 meter per second squared. So we have an acceleration of 4 meter per second squared, just like the way we have an acceleration of 6 meter per second squared here. Now don't forget that this acceleration, we add this acceleration, everything happened. This body accelerated 4 meter per second squared. That for the next 10 seconds, this happened for the next 10 seconds. So you're going to do that plus another 10 seconds. So that means here is going to be 30. Don't forget at first from 0 to 20 seconds, it took it 20 seconds. So that's 20 here. Then for the next 10 seconds plus 10 seconds added to the first 20 here, we end up with 30 on this very second line. So now we're going to solve. Let's see, how do we get acceleration of 4 meter per second squared? Don't forget we said now the new speed, this 120 meter per second for 20 seconds, which gave us 6 meter per second squared acceleration. Now we have a new acceleration, which is 4 meter per second squared for 10 seconds. So let's see how we can get it. Don't forget that acceleration is simply change in velocity over change in time taken. Change in velocity over change in time taken. That's what we have. So the change in time taken is 10 seconds. So what's going to be the change in velocity that will give us 4 meter per second squared acceleration? The change in velocity is going to be 40 meter per second. 40 meter per second over 10 second will give us 4 meter per second squared acceleration. So how do we achieve that? How do we get a change in velocity of 40 meter per second? So that simply means here has to be 80 meter per second, because if here is 120 meter per second, here has to be 80. From 120 to 80, that's a drop in speed of about 40 meter per second over 10 seconds will give us 4 meter per second squared. So that means at this very junction, what we need here is 80 meter per second. We need 80 meter per second. Let me just bring this out for us to understand 100%. We need that means this portion will be a speed of 80 meter per second. Here is going to be 80. So here's going to be 80. So that means the initial speed at this very junction, at junction A, was at 120 meter per second. Then at junction B, the speed dropped from 120 to 80 meter for the next 10 seconds. So that also brought about a change in speed of 40 meter per second over 10 seconds, whereby when you solve it, you end up with an acceleration of 4 meter per second squared. That's just well interpreted. So we have what we need already. So the next thing, now let's see the last part of this question, the last statement. The body maintains the speed attained for 30 seconds. This body maintained the same speed. The speed of 80 meter per second was maintained for the next 30 seconds. The next 30 seconds, this body maintained the speed. So that's going to be plus 30 seconds. So 30 plus 30 is going to be 60. So at point A, we have 20 seconds. At point B, we have 30. At point C, we have 60. Don't forget, 20 seconds. It took this body 20 seconds to move from 0 meter per second to 120 meter per second. So it took this body another 10 seconds to move from this point A to point B, attaining 80 meter per second speed. Then it took the same body another 30 seconds to move from point B to now a new point C. It took this body, so altogether about 60 seconds, 20 plus 10, 30, plus another 30, 60 seconds. So this is how to draw this velocity time graph, as simple as that. So it's high time we solved for other things. So this is the perfect velocity time graph. So let's solve for other questions. So the next question is simply this: find the maximum speed attained during the motion. Find the maximum speed attained during the motion. We've found out already. The maximum speed attained during the motion is simply, as you can see, acceleration, the change in velocity over time taken. That's average acceleration. Acceleration is 6 meters per second squared equals to change in velocity, which is the maximum speed we're talking about, over time taken. So the maximum speed attained during the whole motion, the highest speed attained, you understand, was 120 meter per second. So that's sorted 120 meter per second, as simple as that. So let's look at the next question. The next question is simply find the total distance traveled during the first 30 seconds. The total distance traveled during the first 30 seconds. Now, don't forget that when we talk about distance traveled, right here, we're talking about velocity on the y-axis and time on the x-axis. So for us to get the total distance traveled, as you can see, we have two beautiful shapes here. The first shape here is a triangle. That's a triangle. The next shape here is another small triangle attached to a rectangle. So the next shape we have right here is a trapezium. So this is a trapezium, while this is a triangle. So for us to get the distance, don't forget, it's very simple for us to get the area of the shape. When we get the area of the shape, then easily we're going to get the distance, because right here on this very place we have the velocity, while on this very place we have the time taken. So velocity is equal to displacement over time taken. So if velocity is displacement over time taken, when we cross multiply velocity and time, we end up with displacement or distance. So for us to get the total the distance traveled by this very body in the first 30 seconds, we have to get the area of shape 1 and the area of shape B, which is area of shape A, I beg your pardon, and area of shape B. So by the time we don't get in that, we sum up everything, then we end up with the total distance traveled for the first 30 seconds. So let's get that done right away. So first of all, area of shape A, that's the first thing we're about to work on. So don't forget, shape A is a triangle. So area 1 is half of the base of the triangle times the height of the triangle. Half of the base of the triangle times the height of the triangle. So what's the base of the triangle? The base of the triangle is simply the distance from 0 second time to 20 second time. So that's just 20 seconds. So area 1 is 1 over 2 times 20, then times the height. What's the height? That is simply, the 0 meter per second speed right here at the reference point down to 120 meter per second speed, which is the max height. So that's going to be 120 minus 0, 120. So the height is 120. So this meter per second, this is this meter per second, while this right here is second, meter per second, and this is second. So second, we take our second, we're going to be left with meter. So 2 year 1, 2 year 10. So area 1 will give us 1,200 meter. That's what area 1 is, as easy as that. So right away, the next we're going to get is area of shape B. Area of shape B, that's the next thing. So you're going to get the area of the second shape. The second shape is a trapezium, so that's going to be area 2. So area of a trapezium is 1 over 2, open your bracket, A plus B times height. You need your mathematics skills to be quite up to average level for you to understand and for you to be able to solve this. So area of a trapezium, which is a shape B, this whole shape here, is 1 over 2 bracket A plus B times height. So right away, 1 over 2, what is A? A is the longest side right here. A is 120 meter per second. Then the B is a smaller side. And don't forget, from this very place to this very place is 120. So why from this very place to this very place is the 80 meter per second speed attained. So then times the height. What's the height? Now we have a new height here. This height here right here for this trapezium is the 10-second difference. The 10 second it took the body to move from A to B. As you can see, 20 here, 30 here, which is 10 seconds, times 10 seconds. So what do we do next? The next thing we do is 1 over 2 times 120 plus 80 will give us 200 times 10 in the seconds. So 200 meter per second times 10 seconds. So 2 year 1, 2 year 100. So when we multiply that, we're going to end up with 1,000 meter. So that's that for the shape B. So now let's get back to this very question. Find the total distance covered or traveled during the first 30 seconds. So the total distance traveled during the first 30 seconds is already, we have it already. So the very first 1,200, of the very second 1,000. So total distance, the total distance traveled, the total distance traveled in 30 seconds will give us, we're going to sum them together, 1,200 meter plus 1,000 meter, and that will give us 2,200 meter, which is the same thing as 2.2 kilometers. So as easy as that. So right away, we are heading directly to the very final question. Okay, this is the last part of the very first question. We are asked to get the average speed during the first 30 seconds. Now, I want you to take note of something. There's a clear difference between average speed and average velocity. They're not the same, they're entirely different. If you had seen one of the major lessons, or one of the major lessons we took on introduction into kinematics, then you get to know that there's a clear, conspicuous difference between average speed and average velocity. Now, if this average velocity is going to be changing displacement over changing time taken. Now, since this is average speed, don't forget it was clearly said there that average speed is equal to total distance traveled over total time taken. So for us to get the average speed during the first 30 seconds is going to be simply this. This is speed here. Speed is a scalar quantity. So average speed is equal to distance, total distance traveled divided by total time taken. That's what the average speed is. So now for us to get the average speed, now don't forget we have the total time taken already as 30 seconds. So what was the total distance we got over 30 seconds? As stated out there, the total distance traveled over 30 seconds was 2,200 meters. So the average speed is going to be average speed, total distance traveled, 2,200 meter divided by 30 seconds. So as easy as that. So what do we do next? We're going to divide. 0 cancels with 0. So 3 in 22 is 7. So 21 remainder 1. 3 in 10 is 310. That's 9 remainder 1. Then you have your set of recurring decimals. So our average speed is 73.3333 and so on and so forth meter per second. So that's just that for the very final question in question 1. As easy as that. Okay, it's time for question 2. Let's look at another witty question. This question is simple but very witty and interesting. So look at this. A leaf rises from rest, accelerates uniformly, and then decelerates uniformly to rest through a total height of 30 meters. If the acceleration is twice the retardation or deceleration, and the total time taken is 8 seconds, draw the velocity time graph and find the greatest speed reached or attained. Now, this question is very simple, but it's going to get you thinking. It will get you thinking. It will force you to really be creative. So let's interpret it. The first thing we have to do is to draw the velocity time graph. Now let's see what the velocity time graph is going to look like. Now a leaf rises. We all know what a leaf is. It rises. A leaf rises from rest. That means it wasn't moving. It started from rest. It accelerates uniformly. Uniform acceleration, don't forget what it means. It simply means there were changes in speed, but also equal changes in time taken. So we keep getting the same acceleration at every instant. At every instant, we keep getting the same acceleration. That's what it means. So, and then decelerates uniformly also. Uniform acceleration simply means the same thing as a uniform acceleration, don't forget. But this time around, speed has been lost at an equal rate with time taken. So everything, it took the body passed through the total height of 30 meters, going up and returning, to rest, from rest to rest. So if the acceleration is twice the retardation, and the total time taken for this whole drama is 8 seconds. So let's draw the whole stuff. Let's see what it looks like. So the first thing right here, we're going to draw our velocity time graph. So right here, we have this. And here, we have the time on the x-axis. We have our time on the x-axis. So don't forget that velocity is in meter per second, while time is in second. So let's quickly try to interpret what they're saying here, what this question says. The body started from rest like this, up to this very junction, and after accelerating, the lift accelerated, and after that, the lift returned to rest. So what we can see here is from rest to this very junction and back to rest. So from rest to rest. So from zero, this very place, zero reference, down to point A, then from point A down to point B. So the body started from rest, rose up to this very point, then came back to rest. So let's quickly interpret that. Now, don't forget, a lift rises from rest, accelerates uniformly, and then decelerates uniformly. So the body accelerated from rest up to a given max velocity, with a given max velocity, from no speed at all down to to a very, very given max speed. So let's try to interpret what that is. So it took the body some time. We don't know. We are not told at all. It took the body some time, and we are not also told the max speed the body attained, and that's what makes the question more witty. We are not told that the max speed the body attained, but we knew the body got to a given speed. So let's say the max speed the body attained was m, speed m, and it took the body. Let's say it took the body p second. Let's say it took the body p second plus p second to get to this max m speed. So it's going to take the body another set of seconds, a couple of seconds, to return back from max m speed to return to rest. So let's say take the body q seconds plus q seconds. So that means right here we have p plus q. That's what we have here. So first of all, p seconds, it took the body p seconds to get to max speed of m. So it took the body another q seconds to return to rest. So here we have p at point A, and we have p plus q seconds at point B. So now let's look at other part of the statement. Uniformly to rest through a total height of 30 meters. Now I said the acceleration is twice the retardation, and the total time taken is 8 seconds. So the total time taken is 8 seconds. So if it took this body, if it took the body 8 seconds, so what does that simply mean? It means p plus q will give us 8, which is a form of equation. This equation 1. So you have equation 1. So if you're not good at probably let's say simultaneous equation using substitution method, you find it very hard to understand what we're doing. You understand? So that's p plus q equal to 8. We have that already stated. And we also told that if the acceleration is twice the retardation, we're going to come back to this very question because the body covered the total distance of 80 meters. That's a third thing we're going to interpret. It said if the acceleration is twice the retardation. Now, what does it mean? Let's interpret what acceleration simply means. What's acceleration? Acceleration, a vector quantity, a change in velocity over time taken. So acceleration, so let's see what that is. Change in velocity from 0 to m. That will be m meter per second over time, which is p second. So acceleration is m over p meter per second squared. That's what acceleration is. And let's see what the retardation is. Retardation, which is, let me also call it deceleration. I could also call it negative acceleration, whatever way you want to say it. Is change in what? Velocity. Change in velocity also is the same thing with acceleration. You can see the only difference is that when we have minus, the minus simply shows that the body, was experiencing a sort of a negative kind of movement. Velocity was dropping rapidly. That's what it means. So the acceleration or negative acceleration right here is change in velocity, which is 0 minus m meter per second over time. What's the time? The time is p. The time is q seconds. P minus q, p plus q minus q. So that'll be minus m over q seconds. So we have minus a can take out minus can take out minus. Minus can take out minus. So the retardation is m over q meter per second squared. This is our retardation. So we are told that the acceleration is twice the retardation. Do you know what that means? Acceleration is twice the retardation. So it means m over p meter per second squared is twice, 2 times. Then for you to get the acceleration, you need to double the retardation. So that's 2 times m over q meter per second squared. So this can take out this. So you have m over p 2m over q. That's what we have right here. So what else can we do here? We can interpret this as m. We take out m. So you have 1 over p equals to 2 over q. So if we cross multiply, it means q is equals to 2p. That's what that means. So we can call this equation 2. So if q is equal to 2p, we can fix it right here to get what we are looking for. Q is equal to 2p. So if q is equal to 2p, let's fix it in. So that's going to be p plus equation 2 fixed into equation 1 right here. So that's q, p plus q is 2p. So p plus 2p equals to 8. So what do I have there? 3p equals to 8. We divide both sides by 3. So what do I have? P is equal to 8 over 3. So don't forget that the p is seconds. So 8 over 3, we divide that, now we're going to get 2 over 2 over 3, which is 2.666 seconds. So it took, so that means the first, it took the body 2.66 seconds to attain a maximum speed that we don't know about of m. So we've already known that. So what does q is? What does q I mean? What are we going to get as q? If the p is 8 over 3 seconds, so it means q is equals to 2 times 8 over 3 seconds, which is 16 over 3. We divide that, you're going to get 5 number 1 over 3 seconds also. So we've gotten the p and we've gotten the q. We've gotten the time it took the body to finish off this whole movement. So let's get the maximum speed attained. Now we're going to get that from what they gave to us. We are told that it took the body a total of the body covered a total of 30 meters. The body rose up and also returned. So the total distance covered by this body was 30 meters. So let's get that done. Don't forget, for us to get the total distance for a given velocity time graph, wisdom demands that we get the area. It's very simple, as you can see. We get the area of each of the shapes we have right here. Right here we have shape A and we have shape B. So we're going to get the area for each of those shapes. When we get the area for each of the shapes, then we can get the total distance traveled. So first of all, we have a area of shape A, As you can see right there, they're double. Consider double right angle triangles. In a sense, so area of shape A, I beg your pardon. Area of shape A. So how do we get area of shape A? Area of shape A is very simple. Area 1 is half 1 over 2 times base times height. So 1 over 2 times base. What's the base? The base there is p seconds times the height. The height there is just the m meter per second. So what do we have? 1 over 2 times that's times p times height. That's mp. We have our p already. Our p already is known as 8 over 3. We're going to do that later. So that's mp over 2 meter. That's what the area of shape A is. So let's get area of shape B. Area of shape B, that's the next thing you're going to get, area of shape B. So area of shape B, just A2, area 2, 1 over 2, let's save our time, which is 1 over 2 times base and height. So 1 over 2 times, the base is year to year area of this triangle, shape B. So 1 over 2 times the base, which is q seconds, times the height, which is m also. So that's mq over 2 meter. That's what it is. So we're going to sum up the first area and the second area together, which will give us the total distance traveled. That's total distance as stated out there is 30 meter per second. So let's get it done right away. So mp over 2 plus mq over 2 equals to 30 meter. We are almost home. We've almost gotten what we're looking for. So what do we do next? So it means mp plus mq equals to 2 times this is 60. That's mp plus mq over 2 equal to 30, which is mp plus mq equals to c squared 60. So what do we have? M is common. M is common, as you can see. M is common here. So you have m right here outside. P plus q equals to 60. So m open bracket p plus q equal to 60. So don't forget that the p, which is the first time it took the body to get to the maximum height, which we're about to get, it took it 8 over 3 seconds. And the second time is 16 over 3 seconds. So let's get the maximum speed attained. Let's get the m. So that's going to be m, which we are looking for. Then the p is 8 over 3 plus the q is 16 over 3 equals to 60 meter. So that's going to be m plus m. Open your brackets. So these three are the same. These two are the same. So 8 plus 16 over 3 equal to 60. So you're going to solve that. So m, 8 plus 16 is 24. So 24 over 3 equals to 60. 3 a 1, 3 a 8. So that'll give us 8m equal to 60. Divide both sides by 8. So m is 60 over 8. So we're going to divide right now. So 4 year 1, 4 year 5, that's 15. 4 year 2. So m is 7.5 meter per second speed. So the highest speed attained by the body was 7.5 meter per second. As simple as that. Okay, guys, after all that we've learned today, it's high time we got ourselves tested to see how much we've got from today's lesson. And right here we have about 3 interesting and quite brain tasking questions to get ourselves tested. So the very first question here is: a car starts from rest and accelerates uniformly for 5 seconds until it attains a velocity of 30 meters per second. It then travels with a uniform velocity attained for 15 seconds before decelerating to rest in 10 seconds. Now, the first question: sketch the velocity time graph. Question 2: solve for the acceleration during the first 5 seconds. Question 3: solve for the deceleration during the last 10 seconds. Then the fourth question: solve for the total distance covered during the entire motion. Now, this question was given to some NECO students in 2009. NECO is one of the major exams written in Nigeria. So let's look at the next 2 questions. So question 2: a train accelerates uniformly from rest at a station A to a maximum speed of 80 km per hour and then maintain the speed for a certain time. It then decelerates uniformly to come to a stop at station B, 60 km from A. The time taken from A to B is 1 hour. If the rate of acceleration is half the rate of deceleration, find. Now we have a couple of questions under this question also. Find A, the acceleration in meter per second squared. Then find B, the time during which the constant speed was maintained. As easy as that. So the very last question is this: a body travels in a straight line and a speed at any time does not exceed 5 meters per second. If it accelerates and decelerates uniformly at 2 meters per second squared, find the shortest time required to cover a distance of 30 meters from rest to rest. So these are all the questions that will get us tested on how much we've got from today's lesson. So at this very point in time, we're drawing the curtain of today's lesson. If you found this lesson resourceful, please subscribe to this very channel and share this lesson with others. See you in the next lesson. Thanks.